Good morning, everyone. I hope the midterm went well for everyone. The scores are looking pretty similar to midterm 2 at this point. We'll hopefully have them released by the end of the week. I'll have a few things to say, probably not too much more than what I had after midterm 2, which is, we still have one more midterm. We have a final exam. Final exam is cumulative. So when we get closer to the final, we'll have to start thinking about reviewing some of the content from earlier in the semester. And then, but for midterm 4, let's just try to focus on chapters 7 to 9. We're only covering the first 4 sections out of chapter 7. I'll talk a little bit about ionization energy here on this slide. Then I'll review the other periodic trends that we were talking about on Monday on the next slide. And then we will get into chapter 8 after we wrap up chapter 7 here today. So the goal for chapters as we get into 8 and 9 are going to be trying to determine things about Lewis structures, how can we sketch a Lewis structure, how can we look at a molecule and start to think, does it have single bonds, double bonds? And then when we get into chapter 9, the question will be, how do those bonds and how do the structures of those molecules then adopt some sort of 3-dimensional shape that once we start to appreciate the different sort of structures and types of bonds we have in molecules, we might be able to understand those molecular shapes into chapter 9. Okay, so let's look here at ionization energy. So if we look from left to right, if we go from, say, hydrogen to helium, we get an increase in the ionization energy. And remember, ionization energy is the energy required to remove an electron. So for example, for helium, the ionization energy here is for helium as a gas going to helium plus as a gas plus an electron. So it's the energy associated with losing that one electron from the atom. If you were to look at lithium or beryllium, that's the energy for those atoms losing their first electrons. And you can see that we get an increase from lithium to beryllium. So from left to right, we're seeing an increase. We do have a periodic trend, though, that falls where we call this here the NP1 column. The NP1 column is a little bit lower in ionization energy than the preceding NS2 ionization energy. So if you notice, from beryllium to boron, there's a drop in ionization energy. Then that trend continues where sodium and magnesium increases as we expect. Then we have a decrease to aluminum. So why do we see this decrease here? Well, that just has to do with the fact that we're removing an electron from an NP subshell instead of an NS subshell. So a P subshell is a little bit bigger, further away from the nucleus. So if we're trying to think about how ionization energy is related to the attraction of an electron to the nucleus, it's just not a perfect marker of that trend from left to right. So we just have this nuance that ionization energy is removing an electron from the largest orbital, the one furthest away from the nucleus here. And so when we look at the ionization energy of something like boron, the ionization is coming from a bigger orbital. So when we're looking at beryllium, beryllium's a 2s2 outer configuration, so it's losing one of those electrons. If we look at boron, it's a 2s2, 2p1, so it's losing that electron from that larger 2p subshell, so it takes a little less energy to remove that electron than it did out of the 2s2 configuration for beryllium. So in other words, it's just a configuration anomaly. So we're just taking electrons from a different type of orbital, which takes a little less energy. You can actually measure the energy that boron would require to lose an electron instead from its 2s subshell. We can measure these values through something, though this isn't all that important for you to understand for an exam or anything, but you can measure the ionization energies from all the orbitals from an atom through something called X-ray photoelectron spectroscopy. And if you were to look at the energy required to remove the 2s electron from boron, it's greater than the energy for beryllium. So if we go back to what we were talking about on Monday, as we go from left to right, size is decreasing. Size is decreasing because that effective charge was increasing. So as you go from lithium to beryllium to boron, we're decreasing the average size of those atoms, but then the 2p subshell is a little bit bigger on average than the S subshell was on boron. So it takes a little less energy for the 2p subshell to lose its electron. But then when we continue to carbon, nitrogen, the ionization energy continues to go back up. The general trend for ionization energy, increasing energy from left to right, and then a decrease, then back to an increase. So then why do we see the NP4 column here, the oxygen group, why do we see a slight decrease? Well, if you look at the configuration of oxygen, it's a 2s2, 2p4. And so when we think of the diagram for that, we have something that looks like this. And now spin pairing an electron sort of destabilizes that orbital because there's spin pairing energy. Two electrons that have the same charge going to the same orbital actually destabilizes that orbital. And so then it's going to sort of give us back some, what you might think of as the spin pairing energy we're going to get back when we release those two electrons and we remove one of them. So when we remove this electron here from the subshell of oxygen, it doesn't take as much energy if it weren't spin paired. So that's why you get a little bit of a drop. And these aren't the biggest deal in the world to understand or for you to be able to tell me why you see these configuration anomalies. I just want you to have some sort of an understanding why you get this periodic trend of going up for two elements, dropping, going up for the next two elements, and then dropping, and then continuing to go back up. So the general trend, the general idea is as you go from left to right, effective charge goes up. So that's the main periodic trend. That's the trend that goes up from left to right and then resets every time we start a new row of the periodic table, going back to low effective charge, then increasing. So metals are being characterized by the lower effective charges, non-metals by the higher effective nuclear charges. And then the impact on ionization energy is the higher the charge, the smaller the size, the higher the ionization energy. Okay, and so then if we look at the top to bottom trend, we get a decrease. And so our top to bottom trend for ionization energies, we generally get a decrease. Now there's two counter-opposing trends here. If we think about how we might have expected the top to bottom trend to go, so let me move this over to here. Let's think about that kappa Q1, Q2 equation. Remember how the electrostatic force of attraction is related to this equation here. And so kappa Q1, Q2 divided by D, like I mentioned before, rarely do we plug anything into this equation, but we can use the idea here, of course, that we want plus and minus charges for there to be attraction. So if we have plus and minus charges, then we have a attractive force between those particles. And of course, we have an electron, we have the positive nucleus, so that's our positive negative charge. And so you can think how this is the charge of one of the electrons, and then this charge here could be our effective nuclear charge, the charge experienced by that outer valence electron. And so then you can also then think about how distance is related as we go from top to bottom. So if you're trying to think about your top to bottom trend, you know the size is increasing as you go from top to bottom. And so if you're comparing and you're trying to understand any of the top to bottom trends, let's say maybe helium versus neon. So you know as you go from helium to neon, the size of neon is increasing. So the valence electron's further away from its nucleus, but the effective charge was a tiny bit higher. So if you remember, the effective charge goes up from top to bottom, but not by much. It's a small increase. And so we have a fairly substantial increase in size as you go from top to bottom because we're just adding onto the shell. So that the size trend's a big trend. So as you go from top to bottom, the atoms are really becoming quite bigger in size as you go from top to bottom, but the effective charge increase is not as marked as the increase in size. And so if you think of the increase in size, if I take a negative electron, put it further away from the nucleus, that weakens the attractive force. It's going to be easier to remove that electron as a result. And so if the distance term wins out, then this is going to sort of weaken the energy it takes to remove that electron. And so our reasoning for why the top to bottom trend is the way it is, we get the general decrease due to the increasing size of the atoms from the same trend from top to bottom. And that's despite that we do have a small increase in effective charge with that trend. And so if the effective charge trend had won out, if you said, well, the electron's further away, but the effective charge went up, wouldn't that make the energy of attraction stronger? And you can actually see it does, but only in a few cases. And so it wins out in cases like lead is a little bit higher than tin. This whole group here of the 5D shell are all generally higher than the 4D shell elements. Not that I expect you to memorize those details, but I think you can probably understand that the reasoning why those elements went up from top to bottom compared to the element above them on the periodic table must just be for those elements, their increase in size wasn't as big as their increase in effective charge. So you can understand or hopefully comprehend that it's like a give and a take of how much did the effective charge go up by versus how much did the increase in the size of the atoms go up by. And usually it's the size that's winning out here. So atoms are becoming bigger, so the effective charge isn't as big of an increase, so we have a drop in our ionization energy. So the key details here, let's try to summarize what trends that I hope you understand from left to right for some of these different trends. This is an extra slide I threw in. If you were looking for this, it's just like at the end of the lecture slide page, there's a PDF copy of this one page here. But just to try to summarize our effective charge trend from left to right, This is the big one because the effective charge is the one that gives us the periodic behavior. This is the one that says we get an increase in effective charge from left to right. And this is without any, this is for all elements. Meaning that we don't have any periodic breaks in that trend. If you go back and look at the effective charge, it was increasing from left to right. And so this means as you go from lithium to beryllium to boron to carbon, nitrogen, oxygen, fluorine, neon, that we're getting an increase in the charge that their outer valence electrons are experiencing. That's going to pull those electrons in more closely to their nucleus, and that's going to make those atoms smaller with that same trend. So when we think left to right, the atomic radius, our size of the atoms, is dropping with that same trend. And this is, again, was observed for all elements, meaning, and I'm pointing out for all elements to try to say that there was no periodic break, there was no major inconsistency with that trend from left to right, that we were seeing the decrease in size due to the increase in the effective charge. And then the first ionization energy, we see this general increase, but with that periodic break. So we got this periodic inconsistency. With the MP1 and the MP4. And again, I don't even think I expect that you memorize the MP1 and the MP4, the ones that have this anomaly, but we go up by 2, down, up, then down, zigzag our way across. So we do get, and it's really just, I think, worth pointing out that that inconsistency is not related to an inconsistency with the effective charge trend or the size trend. It's just due to a configuration difference from left to right. So this is just, as we go from left to right, the configurations are varying. We're putting electrons into different subshells, into different environments where maybe they're spin paired or not, and that has an impact on the ionization energy trend. So if you think about the top to bottom trend, for these 3 trends here, our effective charge is a slight increase from top to bottom. And so it's not a very big increase, but we get a slight increase. And the explanation here is that this is kind of coming down to those like radial distribution diagrams that kind of seem like pointless when we were learning about those. But if you go back to like, let's think about, for example, a 4s subshell. Remember how like a 4s subshell would have kind of like a radial distribution function that looks like this, where we'd have 1, 2, 3 nodes. So the 3 nodes, well, maybe the nodes itself, I'm not quite sure why it matters that they have 3 nodes, but it's these probabilities being relatively high for finding that electron relatively close to the nucleus that says even as you have a subshell that's relatively far away from the nucleus, we still have some probability that the electron's relatively close to the nucleus and is going to absorb some nuclear charge. And so if you think that, we have, something in the 4th row would be potassium. So if you get all the way to potassium, you think you have these 18 electrons as part of the argon core, then you have like a 4s1. That 4s1, you may think that there's 17 electrons in front of that outer electron and the nucleus. And the answer is, well, mostly, but there's some probability that that 4s electron is actually pretty close to the nucleus. And so what this means is that the effective charge of potassium is going to be a little higher than +1. And that's going to be higher than you'd expect for sodium, because sodium, while it does have a probability of being close to the nucleus, it's not as pronounced. As you go further away, you get more and more chance of finding the electron, relatively speaking, closer towards the nucleus. So if you think, what percent is the probability that the nucleus is away from the other 17 electrons, that's kind of dropping as you get further away. What I just hope you understand is that you get a slight increase. If you can understand why, that's great. But the real thing to see here is you get this slight increase in effective charge from top to bottom due to just this probability as you get further away from the nucleus that you get like a higher probability the electron's relatively closer to the nucleus than what you might think based on the position on the periodic table. And then the atomic radius trend is that we get an increase from top to bottom without any inconsistency. So we get this for all elements. And then the first ionization energy, we get the general decrease because the size trend tends to win out. So I'd say we get a decrease, but for most, not for all. And the ones that don't decrease, where the few cases, like for tin to lead, for that 5D subshell, the cases where the ionization energy did increase from top to bottom, we can understand that that was due to the effective charge trend winning out for those elements. Okay, one last thing to remind ourselves from last time is this isoelectronic series trend. But anyways, let's look at this isoelectronic series and then move off of our review from last time. So the isoelectronic series trend, this is where you're comparing sizes of things like F- to like sodium plus to things like magnesium 2+, where you pick up for these ions here that they all share the same count of electrons. And so when we're comparing atomic size, we're looking at left to right trends. When we're looking at all these trends up here, we're comparing neutral atoms. So we're looking at the charge of an atom of carbon versus boron versus sodium, where they're uncharged and they all have the count of electrons you would expect based on their number of protons. But whenever we're comparing ions, we want to make a comparison generally based on how many electrons those ions have, because most ions end up being stable around a noble gas count. For example, tens, neons count of electrons. So we see fluoride, even things like oxide form with 10 electrons. So we have 10 electrons for all these ions here. And so if we want to start making a trend of like size for these ions here, we want to think, well, how many protons do they have in their nucleus? Well, that's just the atomic number. And so as you go from oxygen 8, fluorine's 9, sodium's 11, magnesium's 12. You can keep going here to like aluminum 3+ with 13 protons. That having more protons but with the same electron configuration, the more protons, the more positive charge is going to pull those electrons in more closely. So you can think all these atoms share the same idea that they have some positive charge. They have a 1s shell, a 2s, a 2p subshell. So if your electrons in these subshells and you're negatively charged, if you had a higher positive charge to pull you in, you're going to go smaller. So if you're thinking of the size with this trend, aluminum's the smallest, then magnesium, then sodium, then fluorine, then oxygen. So you're making the periodic trend based on proton count. And you can tie this back to ionization energy too. You can tie another trend to this. Think about the ionization energy. The energy, if you wanted to remove another electron, I don't know why you would, but if you wanted to go to Al4+, do you think that's going to take more or less energy than if you wanted to go to O2-? So if you want to take an electron back off of O2, go to O2-. So go to, instead of 10 electrons, go to 9. If you wanted to go to aluminum 4+, which one do you think takes more energy? And again, you come back, you have the exact same configuration. If you're smaller, you have a higher charge, it's going to take way more energy for aluminum to go to aluminum 4+ than oxygen to go to minus. So you can kind of start to base other periodic trends based on what you know about an isoelectronic series and their relative size. And so just think, if you're comparing the size of sodium and fluorine, you use this trend here. If you're comparing the size of sodium plus and fluoride, then you want to use the isoelectronic series trend. You want to say, well, they have the same number of electrons, the one with more protons is going to be smaller. Okay, so there's basically two more topics in chapter 7 that we have to talk about. The first one here is how we determine the configurations of ions. And then the second topic is going to be the fourth periodic trend for electron affinity. So let's talk about electron configurations here. So for cations, this is maybe not going to be entirely intuitive, and we're going to have to make sure we understand why this is, but the electrons are going to be lost from an atom from their largest orbitals first. And if you think about the electrons that are going to be most weakly held onto, if you start thinking of an atom, the electrons that are further from the nucleus are going to be the electrons that experience the lowest overall effective charge. So the electrons that are furthest away are going to have the weakest attractive force because they have all the other electrons in the way that are absorbing some of the positive charge. And so the weakestly held onto electrons are going to be the ones furthest away from the nucleus. When we think of calcium, this is pretty easy because when we look at calcium's configuration, it has an argon 4s2 configuration. So if we're taking 2 electrons off of calcium, probably not too crazy to think we have the argon configuration, then a 4s2. The 4s2 electrons are the biggest. We lose those 2 electrons and just simply have the configuration of argon. So you have a 1s2, 2s2, 2p6, 3s2, 3p6. If we want to write that out, that's fine, just to make sure that we're on the same page of what the argon configuration is. And so calcium 2+ is just the configuration of argon. And it's that noble gas configuration that makes a lot of ions, especially the ones close to the, if we're 1 or 2 off, or maybe 3 in the case of aluminum. If we're relatively close to being a noble gas, we lose those electrons, come up with that same configuration. That's what we see, a lot of stable ions existing with that configuration. Now, if we go to titanium, So, and really, if you're going to do a configuration of a cation, you almost always have to go to the neutral atom first. So let's look at titanium with no charge. The configuration of titanium, it's just to make sure we're looking in the right spot. It's 2 over from calcium. So its configuration would be argon, 4s2, 3d2. Now, you would think that the 3d2, since we kind of last put the 3d2 into the configuration in terms of the way we wrote the configuration, in terms of the way we think of the D block, we're kind of putting those electrons in last, but we don't take them out first for the cation configuration. For the cation configuration, we come back to the electrons that are the biggest. And this kind of comes back to the idea of, well, where are the 3d electrons first? Where are the 4s electrons? And so if we think of sort of having a positive nucleus, and for maybe titanium, we're thinking we have the 1s2, the 2s2, the 2p set of orbitals, the 3s2, the 3p set of orbitals. Oops. So the 3p set of orbitals here. And then the 4s goes here. So that would be what calcium looks like. We have the 4s electrons and this outer 4s electron. Those are the 2 we lost for calcium 2+. But then for titanium, we're putting 2 electrons in an orbital that looks like this. We're putting maybe an electron in that type of an orbital, maybe one sticking out of the plane of the page. I won't sketch, it'll make things hard to sketch, but we're putting the 3d subshells closer to the nucleus than the 4s. When you think of the 3s, the 3p, the 3d subshell, those are occupying the same relative space. The 4s is even bigger. The 4s, the 4p, the 4d are going to occupy the n=4 level, n=5 further away, etc. And so the largest orbital is the 4s. And so that's going to have to be the orbital that we lose electrons from first if we make a configuration for titanium 2+. So the configuration of titanium 2+ should be argon 3d2. And this isn't like an anomaly, this is just the rule. So the way we lose electrons from atoms to make cations is we lose them from the largest orbitals, and the largest orbital is always going to be the one with the biggest n, and then if you have multiple orbitals at the same n value, the one with the greatest L value. So in other words, a d orbital is bigger than a p orbital, and a p orbital is bigger than an s orbital within a given subshell. And so to write that out, that would mean that a 3d is bigger than a 3p is bigger than a 3s. But then a 4s is bigger than the 3d. So the 4s is bigger. This isn't in terms of energy, this is in terms of size. So in terms of energy, though, the 4s was lower in energy than the 3d. That's why calcium filled into the 4s first. So energetically, the 4s, then the 3d, but in terms of size, 4s bigger than the 3d. Okay, so then if we go to titanium 4+, we have to take 2 more electrons away, then we have no other choice but then to take the 3d subshell next. So then we start thinking you have, in part of the argon configuration, you have the 3s, the 3p, you have the 3d, the d is the biggest subshell. So you take from the greatest n with the greatest L in that order. So we'd go to just the argon configuration for titanium 4+. Now let's come back to titanium 2+ and calcium 2+ for a minute. So for calcium, the thought for calcium was probably the atom itself could have been choosing, do I want to put 2 electrons closer to the nucleus where they repel the other electrons? These d electrons are having repulsions with their neighboring p subshells. That's bad. But then being further away from the nucleus is also bad because it's further away from the nuclear charge. So you can kind of see the atoms have a give and a take situation. It's like, do I want to put 2 electrons closer to the nucleus so they experience greater charge but greater repulsion? So it must be that the repulsions for calcium are so strong that it put the electrons into the s subshell. Then for titanium 2+, it must be, well, if you made that charge a little higher, instead of being an 18+, or excuse me, a 20+ for calcium, titanium's a 22+, so you make the nuclear charge a little higher, then that keeps the electrons in that d subshell preferentially instead of letting them stay in the s subshell. So as you're making cations, the difference between neutral atoms is the overall charge is higher. So you have a little bit more of a propensity for atoms to stay in those smaller subshells where they have more repulsions with their neighboring electrons because they get to experience that greater charge in return. And so if we look at iron, the configuration, if we went, and this is really where a question from chapter 7 would come in, is it might say something like, what's the configuration of Fe2+? What's the configuration of Fe3+? Another way we'll ask this is to show a diagram, like show an electron diagram of how many unpaired electrons the ions have. But the thing you almost always have to do is go back to the neutral atom. So you really want to, if you see a question like that, go back to iron neutral. The neutral configuration of iron would be argon, and it's 6 across, so it should be a 4s2 and then a 3d6. If you start getting worried about is the configuration an anomaly? Remember how some configurations could have anomalous configurations? Well, when you're coming up with cation configurations, it almost wouldn't matter if you had the right configuration or if it was anomalous. If you're taking electrons away to go to like a 2+ or a 3+, you're going to notice that it won't matter if you have the anomalous configuration or the expected configuration. For iron, this is its real configuration. So we don't really have that problem with iron of knowing what its configuration is. But if we're taking 2 electrons away, the largest ones are removed first. So the configuration of iron 2+ would be argon, 3d6. And then iron 3+ just takes 1 away from the 3d. So we'd have an argon, 3d5. Now a couple double checks would be go back to the count for iron 0. The atomic number for iron is 26, so we should have 26 electrons assigned. So we have 18 for argon, plus 2 plus 6, so that's 26. And if you go to iron 2+, you should have 24 electrons assigned, 23 for iron 3+. And so we have 18 here, plus 5. So you can always double check how many electrons the ion should have versus how many you've assigned. And if you're ever stuck, just go back to the neutral atom and just take 3 electrons away in the order from largest. So the 4s2 first, then the next largest, the 3d. And so the last thing you might do is just do a configuration. So a 3d6 should be 1, 2, 3, 4, 5 for the 3d subshell. 1, 2, 3, 4, 5 spin up, and then 1 spin down. So we have 4 unpaired electrons for iron 2+. Then we have all 5 of those electrons spin paired in the same direction for iron 3+. So 5 unpaired electrons for iron 3+. And so a test question might say something like, well, how many unpaired electrons does, manganese 2+ have? And then you just have to think, well, what's the configuration of manganese 0? What's the configuration of manganese 2+? Then how many electrons are unpaired? Anions are actually pretty easy because we actually just put electrons in, continuing the order we would have expected from our base configuration. So for oxygen, as an example, we'd have a 1s2, 2s2, 2p4 configuration. And so in terms of a diagram, we have something like this. And I didn't maybe have to write the 1s2. I could have written helium, 2s2, 2p4. So that would be fine too. If you just go with the condensed configuration, we could have written it that way as well. But 1s2, 2s2, 2p4, and so O- just adds 1 more electron. So we go from having 8 electrons to 9 electrons. So we go from a 1s2 to a 2s2, 2p5. So we're just putting 1 more electron in. So we have our 1s2, 2s2, 2p5. And then O2-, not surprisingly, 1s2, 2s2, and then 2p6. So capping off the n=2 subshell with the last electron. And so then why does O3- not exist as a stable ion? O2- is that's the oxide ion, pretty common ion. Why is O3- not stable? Because we'd have to put an electron into a 3s subshell that's a lot higher in energy. That's just not energetically going to be favorable or feasible for an atom to do. And then when we get to argon, to kind of show this too for argon, it's the 1s2, 2s2. Let's actually do the configuration relative to neon to save some writing. So it would be neon, 3s2, 3p6. And so the configuration for argon minus would be neon, 3s2, 3p6, and then a 4s1, just into the next subshell that's higher in energy. And now that's not going to be easy. That's not going to be favorable to put an electron into a 4s subshell because that's a lot higher in energy. If we're filling into the subshell that the atom's existing in, that it has an open valence shell in, that's going to take much less energy than putting one into a higher energy subshell. But then that leads us into the last category of periodic trends, which is the electron affinity. So electron affinity is the energy associated with absorbing an electron. So if we look at that for, say, F, the electron affinity for F is the energy associated with the atom. And all these atoms are assumed to be gaseous, just so that we're comparing just the energy difference between the ion and the neutral atom. But it's the energy difference between F minus and F plus an electron. And that's equal to minus 328 kJs per mole. So the delta H of this reaction is equal to our electron affinity, which for this atom is minus 328 kJs per mole. And this is negative. Like, that's good. That means that if we take an electron off of something and put it onto fluorine, that we get energy back. That takes energy downhill. Going towards a lower energy is good. That's what atoms want to do. They want to generally take some high energy structure, form some low energy structure as a result. And so if you look, the most negative values are the halogens. So the halogens have the most negative electron affinities, which kind of makes sense because they're the ones that are most likely to absorb an electron and exist as that -1 charged state. So F minus, Cl minus, Br minus, I minus, very common ions. We've seen these a lot. And then, of course, we've never encountered helium minus or neon minus, argon minus in any kind of stable compound. That's because it takes so much energy to create that anion that there's no cation we can make that would energetically make that favorable to occur. And so it just takes too much energy. So our least favorable group are the halogens. So these are the least favorable electron affinities. So in other words, the most positive electron affinities. In fact, they're so positive they're hard to measure. You don't even see an actual number reported with them. And so our left to right trend, the electron affinity is more negative towards the halogens. So we're becoming more negative towards the halogens, and we reset with the highest value being the noble gases. So the hardest element that there would be to add an electron to would be the noble gas group, being very high in electron affinity, and we're becoming more negative away from those elements. So most favorable for the halogens. Next most favorable group, if you notice, is the neighbor of the halogens, the oxygen group. So the oxygen group tends to form negative ions very commonly, but they'll tend to form the 2-, so we'll tend to go all the way to O2-, S2-, etc. The nitrogen group is not as favorable, but we actually have another configuration anomaly situation where nitrogen, to add an electron, has to spin pair the electron, which causes destabilization. And so when you look at oxygen, it's spin pairing an electron too, but it's also spin pairing an electron to a smaller atom with a higher charge. So it's spin pairing, but more favorably. Fluorine, it's spin pairing an electron, but also to an even smaller atom with an even higher effective charge. So fluorine's like perfect in this situation, has room for one more electron. It's really small, has a really high effective charge. And so what we need for electron affinities to be on the negative side is we want the size to be small, so that's good for fluorine. We want the charge to be really positive, that's good for fluorine. If you notice, chlorine's even more negative than fluorine. Why would that be the case? Well, interestingly enough, if you think of the effective charge of chlorine, it's higher, but chlorine's bigger. So it's interesting here that it's actually the effective charge trend winning out. So the effective charge of chlorine being higher means it can absorb an electron even more favorably than fluorine. Not that I don't think this is really worth memorizing, but if you look at the top to bottom trend, it's really the third row of the periodic table that tends to be the most negative compared to the atoms above and below. This is just showing you the give and take of the trend of size versus charge. And that there's really no way necessarily we could have predicted that this trend would have went this way, but it's just showing us that for the third row, it must be that their size increase isn't as big for the anion as it was for the neutral atom. So the ionization energy trend dropped from top to bottom. Here the electron affinity trend is a little bit more chaotic, or it's a little bit more towards where the third row is the best in terms of the balance between their relative size and effective charge. Okay, so left to right trend, more negative towards the halogens. The NP3 group is more on the positive side. That's because it's spin pairing an electron for the first time. And then the beryllium group is on the positive side as well. A little bit of an anomaly. If you look, we're negative, but then positive, then we drop, and we go back. So we kind of do this trend here of zigzagging like we did for the ionization energy trend, but here we're zigzagging with the NS2 group and then the NP3 group, because the NS2 has to put an electron into a higher energy subshell, the NP subshell, and then the NP3 is spin pairing an electron for the first time. So we're seeing configuration anomalies, much like we did for ionization energy, but on the other side. So on the NP3 and the NS2 side. Again, I probably don't expect that you memorize that detail of that fact that it is the NS2 and the NP3, but hopefully that you can comprehend that the thing that's going on here is just the anomaly of where the electron's going from left to right is not consistent. So the electron's just going into different types of environments as we go from left to right, but generally towards a more highly positive atom and a smaller atom from left to right, so therefore more negative, but stopping at the halogens, resetting with the noble gases. And lastly, just say it one more time, noble gases are the least favorable. So they're the ones that are going to be least likely to absorb an electron. Now you can also say the metals are not very likely, even though if you notice most metals, or a lot of metals, are negative in their ionization, in their electron affinities. So why does Na minus, why does sodium minus not form in any kind of stable compound? Well, this in a way will lead us into chapter 8, where we talk about lattice energies and kind of like what the attractive force between a plus and a minus particle are. But if you think of like Na minus isn't necessarily so bad, but what's bad is the energy it would take to get the electron from something like fluorine. So if you had sodium and fluorine, and in a way this is going to lead us into chapter 8, but picture sodium and fluorine, and just let's picture maybe gaseous atoms so we don't have to worry about the physical state of fluorine being F2 as it's stable. So fluorine usually exists as F2 as a gas, sodium usually a sodium solid. But let's just imagine a gaseous sodium molecule, or excuse me, a gaseous sodium atom encounters a gaseous fluorine atom, and that they're trying to decide who gets the electron. Well, if you remember, the ionization energy of fluorine is really high. So the ionization energy of fluorine is very, very high. So it takes a lot of energy to remove an electron from fluorine, and if we put that electron onto sodium, we get a little bit of energy back. And so if we wanted to go to sodium minus fluorine plus, you're probably thinking it's going to take us probably over 1,000 kJs per mole to create this cation, and then in return we get back 53 kJs per mole for putting the electron onto sodium. So that's not great. Is there a better alternative? Well, what if we take the electron off sodium, go to sodium plus, because that only takes about 500 kJs per mole. So that's about a third. If we go back to the ionization energy slide, if you look back, the ionization energy of sodium is probably about 1/3 or even less than that of fluorine. So it doesn't take as much energy to get the electron off of sodium. Then we put the electron onto fluorine, we get back 328 kJs per mole. So we're only kind of like plus 150 kJs per mole uphill to make these charges here. And then we're like plus probably 1,500 plus kJs per mole to create those charges. Once we make the charges, you then have the electrostatic force of attraction. So which force of attraction is greater? Well, that's a complicated question, but let's just maybe throw out the possibility that they're probably fairly similar. That if you had a minus and a plus versus a plus and a minus, that attractive force would probably be pretty similar. So it's going to be better if it takes less energy to create the ions, is the point here. So these are going to be the charges sodium and fluorine adopt, because the ionization energies on the left side are much lower than the ionization energies on the right side. Then the right side elements have much more favorable electron affinities than the left side elements. So it's about the give and the take. The give and the take's better. It takes less energy to create the plus and the minus if we put the plus on the metal, the minus on the non-metal. Probably pretty obvious that would have been the case. But if you were looking at the ionization energies or these electron affinities here for sodium and potassium and saying, hey, they're negative, why don't we make sodium minus? The answer, or the issue isn't that that's unfavorable to do so in and of itself. It's about the range of possibilities. It's to do so requires an electron to come off as something that takes way too much energy. Okay, so that will, let me show you a couple of group trends. There's just a couple of things I wanted to show. These are from later sections in the book, so these aren't things I would worry about for the exam, but I just wanted to show you two quick trends here for melting point trends. So this is looking at the melting points as you go from top to bottom. And I think this is interesting. I don't think, if I had asked you to predict if cesium or lithium would have the higher melting point, I bet you would have predicted cesium, just because cesium's bigger. We have this idea sometimes that atoms or things that are bigger have like higher boiling points and higher melting points. But as you can see here, the melting point of cesium is actually just above room temperature. If room temperature was 30 degrees C, we would be talking about how there's 3 elements that are liquids at room temperature. Remember, it's bromine, Br2 is a liquid, mercury is obviously a liquid, and cesium is almost a liquid. Its melting point is just above room temperature. I think we'd have 4 if room temperature were 30. I think gallium has a melting point also in this range. Anyways here, melting point decreasing from top to bottom. I think it's interesting for you to see that. If you look at the melting point trends of the alkaline metals, same basic trend that you get a decrease in melting point. You get a little bit of a weird anomaly here where you kind of go down, then back up. But just kind of generally seeing melting point trends for our metals are decreasing as we go to a larger metal. This is also showing you the ionization energy trends are decreasing as we kind of were showing you earlier. The I1s, the first ionization energies are decreasing from top to bottom. But then let's look at the nonmetals. And I just wanted us to see something that we probably already know, because if you go from F2Cl2 are gases, Br2 is a liquid, I2 is a solid, that must mean the melting point's increasing from top to bottom. That's why I2 would be the solid and not F2 at room temperature. And so we have an increase in the melting point trend from top to bottom. And then the same thing can be seen for the noble gas trend, elements here. And then I was even seeing some weird discussion on Reddit yesterday on how oganesson, which is that element 118, that if it were to exist in enough quantity to collect, when you make these like really heavy elements, you can only make 1 or 2 atoms at a time and barely prove their existence, and physicists have all kinds of crazy ways to detect the formation of those atoms. But you're never making like bulk quantities of like element 118 when you synthesize it in a physics experiment. You create a handful of atoms that have a very short lifetime. But if you could collect it, if you had a scenario where you can make a bunch of it, it's predicted to be a solid and not a gas. And it's because it's so big. As you keep making atoms bigger that are non-metallic, eventually you can increase you're increasing your melting point with size as you go from top to bottom. So the boiling point trend's increasing here. Boiling points and melting points go with the same trend generally. So if the boiling point increases, so too does the melting point. So I think there's something interesting here. I think it's interesting that the metals are decreasing and the nonmetals are increasing in their trends. This is going to be something I think that's important to start to think about, which is when atoms are exchanging charge, it's better to do so when those charge centers are small. So what lithium does is it's sharing its valence electrons across all the nuclei in a lithium block. Same thing with cesium. It's sharing its charge across all the sort of nuclei in a block of cesium. The issue with cesium is the atoms are very big. Lithium is very small. It's better to be small when we're exchanging charge. So when you think of charge, that's like kappa Q1, Q2 divided by D. D being small means higher energy of attractive force. But when you look at nonmetals, they don't have charge to share. When you're looking at 2 noble gas atoms, an argon atom versus an argon atom, there's no charge being really transferred between those 2 atoms. They have to somehow inductively create a charge between those 2 atoms. They have to somehow induce their electrons to move in such a way to create a charge. We'll talk about in chapter 11 what that actual effect is and how to understand it a little bit better. But for the nonmetals, they don't have the built-in charges. They have to induce those charges in themselves, and it's easier to do that when they're larger. So for nonmetals, increase as you get bigger, melting points go up. For charged substances, it's the opposite trend. Being smaller is better. I just want us to see that trend. I think it's important to understand that difference and to start to see that that's the case here. Okay, let's get a quick start into chapter 8. And one of our things that we're going to see hopefully early on is coming back to the issue of like plus and minus, why compounds form with those charges. And then even if you look at if you're going back to like the Na and the F example we were talking about, if you can sort of picture that it takes 500 kJs to create the cation, we only get back 328, we make the anion. Why did that form? Because that's uphill in energy. We have to then see how the electrostatic forces of attraction lead the compound to gaining stability through that electrostatic force of attraction. So chapter 8, we're going to talk about some bonding in ionic compounds, and then more to the point of chapter 8, we're going to talk about a lot of different ways a lot of different compounds we can sketch Lewis structures of. So we want to talk about Lewis structure rules, so we can sketch a bunch of Lewis structures, so we can then get into shapes and properties of molecules in chapter 9. Okay, so in chapter 8, the basic sections are here. So we'll talk about like Lewis symbols, octet rule, lattice energies, ionic bonding for the first couple sections. And then we'll get into the covalent bonding, the non-metallic compounds, their structures. We'll talk about bond polarity, electronegativities, and then Lewis structures to kind of wrap up the chapter for a lot of different type of compounds. Okay, and so there's 3 basic types of chemical bonds, 2 of which we'll talk about in this chapter, but I did want to mention that in addition to ionic bonding and covalent bonding, we also have metallic bonding. When I think, or if I write something like Fe solid, you may not think that there's bonds between Fe atoms and Fe solid, but of course there are. The things that hold iron together are what we call metallic bonds. Those bonds are relatively complicated. We'll talk about these very briefly in chapter 12, but I just want you to picture that if I say something's a solid, there has to be something holding the solid together. So what holds the atoms together in a metal is metallic bonding. Ionic bonds would be something like NaCl. So the things holding sodium chloride together are the electrostatic forces of attraction of the plus and minus ions. So ionic bonding is the electrostatic attraction of those ions. And then covalent bonding is the bonding in things like CH4, water, etc. So it's the bonds that are holding the atoms together within a molecule. So those are covalent bonds. And so ionic bonds, electrostatic forces of attraction. In the case of covalent bonds, these bonds here are covalent bonds holding the H together to the O in water. So that's our covalent bond. If you then get into, if you remember learning about hydrogen bonding, dipole-dipole forces, we'll talk about those in chapter 11. That's what's holding and those are the attractive forces in like liquid water or solid water. So there can be attractive forces between molecules that are covalent or covalently bonded. We call those intermolecular forces of attraction. We'll talk about those later. But the things holding the actual atoms together within a compound are either ionic bonds, covalent bonds, or metallic bonds in their simplest form for some key types of compounds. And it's going to be, the ionic and covalent we talk about mostly in this chapter here. Okay, in terms of the, coming up with like a Lewis symbol, we usually look at the sort of position on the periodic table, get a sense of how many valence electrons an atom has. So if we're, looking at something like, lithium, we have 1 valence electron, beryllium has 2, boron has 3, 4, 5, 6, 7, 8 across in terms of their valence counts. Those are coming from, if I just look maybe at nitrogen, a 1s2, 2s2, 2p3. So these are the outermost electrons. That's the outermost shell. So that's our 5 electrons that we say nitrogen has in terms of its valence. So if I'm writing a Lewis dot diagram for nitrogen, I probably write this symbol this way here to kind of try to show like the 2s2 and the 2p3 here. Now for carbon, being a 1s2, 2s2, 2p4. So if I look at carbon, I have the configuration here, I don't need to rewrite it. Carbon's configuration 1s2, 2p2. So carbon 2s2, 2p2, so 4 valence electrons. Now I have 2 ways I can write the Lewis structure. I can just take the 4 and write it around each of the corners of the atom. So I can take carbon and just write something like this, or I can write it like this. It's really not that big of a deal where you put the dots, other than maybe alluding to some different types of Lewis structures later that might be useful if you have one of the 2 different types of dot structures. But so a Lewis dot diagram is just from making sure you have the right number of dots for the valence electrons, and then where you put them isn't that big of a deal, other than I usually, would only put 2 on a side, so instead of putting more than 2 on a side. So, and so then the most you can get according to, if you go to the octet rule, or just the idea of there being 8 would be up to neon, where we get all 8 filled. So expanding that octet or expanding past 8 is going to be tricky to do. Now the octet rule, being kind of the rule that atoms are striving towards a count of 8 valence electrons, is maybe not necessarily the best rule in a lot of ways, because there's a lot of ways you can sort of say that the atoms are actually striving toward either complete shell, because obviously helium's not going to get to 8. Helium's happy with 2 valence electrons. So a better rule would be kind of like capping a shell off or filling whatever valence shell you happen to be in with electrons. But another rule that we're going to see is there needs to be like a relative charge balance. It's going to be hard for an atom like nitrogen. Like nitrogen 3- does exist, but it's not that common. We're going to see nitrogen in a lot of different compounds doesn't get to 8 electrons surrounding it with a negative charge of 3-, but through sharing electrons through covalent bonding. So we're going to see in a lot of ways atoms tend to be almost happier, if you will, if they don't have too much of a charge built up on them. So we'll talk about something called formal charge, and that in a lot of compounds, the formal charge tends to be 0 for most elements, and if it becomes really, really high or really, really positive, there can be usually other structures that can adopt, or maybe other ways that that compound can form other types of compounds that reduce those charges. This slide here is showing you the idea of taking sodium and chlorine in their elemental form. So sodium solid, chlorine 2 as a gas. If you introduce them together inside of a container, they will react together fairly violently to produce sodium chloride, because a lot of energy is going to be given off in the process. And so again, coming back to the question of sodium, takes energy to ionize, chlorine gives energy back, but it's not necessarily exothermic yet. Where does the exothermic nature in the reaction come from? Well, it's going to come from the electrostatic force of attraction being really strong. And so let's take a look at the next slide. It gets into the concept of ionic bonding, where metals have our low ionization energies, or relatively speaking on the periodic table, the lowest of the ionization energies. I was just thinking there's something I forgot to mention on the ionization energy slide, so I'll just mention it here. If you look at hydrogen, hydrogen's really high in ionization energy. So why, when we look at metals, why is hydrogen not a metal compared to lithium and the elements below? If you go back to the ionization energy chart, if you just think about its ionization energy, H's ionization energy is 1,312 kJs per mole. And then lithium's, I think, 496, or it's around, let's say, 500 kJs per mole. And then the other alkali metals below are even lower. So hydrogen's ionization energy is 2.5 times that of lithium. It takes so much energy to get the electron off of hydrogen, it's never being removed from the atom. So the best thing hydrogen can do is it can share its one electron with another atom to make H2. And then two H2 molecules, they're not going to be attracted together. Lithium, it's like that electron's so loosely attracted to that nucleus that it just shares it with the block. So if you look at a block of lithium, you can sort of see almost the electron, that valence electron for all the atoms are just being shared with each other. And so that none of the atoms really own a valence electron the way hydrogen wants to keep its electron by its nucleus at all times. It doesn't want to give it up. So that's really the difference between hydrogen and lithium and the other alkali metals, is this high ionization energy. It doesn't allow hydrogen to share its electron with other atoms other than one other atom. So it can share with one atom, that's good, but it's not going to share it with a whole block of hydrogen to make a metallic hydrogen sample. So again, metals, low ionization energies, hydrogen not low, so it's not one of the metals. And then non-metals, these are the ones that generally have the most favorable electron affinities, the most negative electron affinities. And then cations and anions, once they are formed, have this electrostatic force of attraction. And so the electrostatic force of attraction, we keep rewriting this equation, but kappa Q1, Q2 divide by D. So once we form that bond, we get this energy of electrostatic attraction that's really strong. Let's get a sense of just how strong that attractive force is. We measure that through something called the lattice energy. So the lattice energy would be the energy it takes to take that solid ionic compound. So like, let's take sodium, solid, Cl2, let them form the compound that they forms a solid that you then characterize as being NaCl, Na plus Cl minus. And then you take that compound and then ask the question, how much energy does it take to separate those ions into their gaseous ions? So let's take the solid ionic compound and then convert it into its gaseous ions. Why gaseous? So that the ions are far away from each other, and so there's no interactive forces between the ions. And so this is going to give you a measure of our ionic bond strength. It's telling you how strong that ionic bond was because it's telling you how much energy it takes to separate those atoms. So it's 788 kJs per mole. So that's a lot of energy. It takes a lot of energy to separate those ions. So in other words, if you were to take sodium and chlorine, exchange their electrons, make sodium plus and Cl minus. So from sodium gas, chlorine gas, 500 kJs up to make sodium, 350 back to make Cl minus. You make the Na plus, the Cl minus, they turn into the solid, you get 788 kJs per mole back. So that's the driving force why sodium chloride forms, is this lattice energy, just how much energy it then takes to separate the ions once they're formed. Or if you think of flipping the reactions, if you have these ions, you want to form the solid, that's minus 788 kJs per mole. So a lot of energy back when we make those ions. So lattice energy is the energy that has to be absorbed to break the ionic bond. It's a measure of ionic bond strength. This shows us a chart. I'll talk about that next time. I just want to show this trend here to wrap up. If you compare sodium chloride to lithium chloride, remember with charges, being smaller is better. If you make lithium instead of sodium, notice that the lattice energy goes up. If you make the metal bigger, you reduce the lattice energy. That's because if you make the distance bigger away, the attractive force drops. And so the same thing happens if you change the size of chloride to fluoride to be smaller versus bigger. There's a change in charge. So the closer we can make ions together with the same charge, the stronger the lattice energy, the more energy to separate. If we make the ions bigger, the weaker the attractive force, the easier to separate. We'll come back to this idea. We'll build from this next time. All right, guys, have a great day.